Hello everyone, this is Hossein Mukhtarzadeh. And first of all, I would like to thank the organizers and the committee to help us present today. This is about self-paced treadmill control algorithm. And you can see here that the preprint is available. You can go ahead and, if you're interested, have a read. And there are quite a lot of information here as well as supplementary. And we shared our company's self-paced algorithm. First of all, I would like to thank, before I start talking about algorithm, my co-authors and everyone who from the our development team and management to help us share all these details with you. So why self-paced and treadmills? So, you can actually have a treadmill set to speed, but this might not be the comfortable speed for your subject. Imagine your subject moves quite fast or maybe slower, so you'll end up at this age or maybe this age of the treadmill. Then what we want to bring them is while they're walking quite smoothly and in their comfortable speed, we bring them quite to a quite safe or middle of the treadmill. So that's somehow the reason we do self-paced treadmills. There are quite a lot of, not a lot, but some other methodologies. People have used force plate data or getting a center of mass. And then from that, using like a Kinect sensor or 3D map sensors, or like what we did, a PD controller type of thing or nonlinear control to predict and try to calculate the delta speed that matches with the gauge speed. So this is one of our old algorithm that we had. We already had shared this. You can see here that two situations, a person walks from a certain speed, and then, as the person moves distances, the gauge speed is a steady state. So this is the acceleration, and it is PD controller. You can see here the relative displacement, the proportional one, and the differential one, like the speed as well, the velocity of that person or relative, and to the relative, which we call it differences of the subject's position and the middle of the treadmill. But what we are interested and what we want to know as a company is we didn't want to this person to be quite close to the edges. First of all, it's not safe, and we don't want them to just go back and forth all the way. And when they are here, we want them to have as quickly as possible and as smoothly bring them back to kind of this green area. So we call them normal correction and fast correction. So we'll see what I mean and how we actually do these type of corrections. So to achieve that, we basically define three different accelerations. So these A stands for acceleration. They Kelvin calculated. So we can calculate all these three accelerations, A of P and V and S. So each one refers to a specific acceleration. For instance, the first one is the position one. That's similar to what we had before. Like we had before, position and speed. Like Z refers to the displacement from the center of mass, to the center of the treadmill. And these two are like sensitivity and the gain, as you know from the controller design. So this A of P is related to the proportional one, and A of S is related to, you can see Z dot and the Z of F. So this is similar to what we have the old version. But here is the key thing that help us achieve the things that we had. I mentioned to you that not going toward the edges, and if it go to even toward the edges for any reason, then we can slow it down, and then it was quite before there it can stop. So you can see here we have divided by 2 d, and so d is a displacement from the edges to the center of mass. So if this d is very small, then the acceleration becomes quite high, so which means that this person can be brought back to the center quite fast. So that's what we call a fast correction, and these two terms will be effective in this region as well, right? So that they can do just quite quick adjustment, not very fast one. Then when we calculate this at any given point, and we calculate the accelerations, we can do the integration, and at any given point again, you can see A of d the dt, then the delta speed will be calculated. This delta speed now is quite close to what the subject's gauge speed is. You'll see now what I mean. It's quite easy to implement this. So we implement them in our devices, in all our devices. What we do, we just get 4 pelvis markers, and you can see the belt speed is going all the way versus time to be close to basically sort of match with the gate speed. So here's what you notice. I start the system and then I activate the self-paced, and then the belt speed all the way goes to a steady state based on the center of mass position that we calculate using, for instance, the markers around the hip. So I've created quite a lot of tutorials if you like. I don't play this all here, but if you are interested, you can actually go to this link and learn more about this. Our customers basically have used it extensively. So you can see here over 400 subjects have been used in the different population and different devices that we have that have used our ADIS algorithm and implement them and use them. So here's an example that I created in MATLAB for you if you don't have our devices. So first we calculate the center of mass, we then calculate the speed of it, and then the belt speed as I mentioned. You can see different types of belt speed, and then we calculate the overall belt speed. This is acceleration and then belt speed. You see that the sensitivity can change so that people in different population, maybe it's different, so that you see that the steady state can achieve in different sensitivities differently. So we shared experimental data, the MATLAB codes that you can recreate all these things, and even the flow, the process that I mentioned here. If you are interested in what we do, I'm giving a free TFlow workshop just in a couple of weeks. Use this link or just scan here, and I would be glad to see you all there. Thank you very much and hope you enjoyed. I'm happy to take any questions.